In this movie, I'm going to discuss the angular overlap model for determining the splitting of the d orbitals and determining the energies in general for the orbitals in a coordination complex. This model basically estimates the degree to which the d orbitals are increased in energy and the ligand orbitals are stabilized in energy based on the amount of overlap between those two orbital sets. The reason this approach is so nice is because it can handle a lot of different geometries and in fact take into account both sigma and pi bonding interactions to pretty quickly generate molecular or diagrams of the orbital energies for the metal complex. So in this example, we're going to first just consider sigma bonding interactions. This table is from your textbook. It shows it's table 10.10, angular overlap parameters for sigma interactions only. And what we're going to do is use this table to help us generate a orbital diagram for an octahedral complex first as our first example. So first we're going to, just as we did in some of our MO diagrams previously, we'll put in the d orbitals. The s and p orbitals will also be involved in bonding in a metal complex, but they will not be shown in this diagram. It's a somewhat simplified. So we'll put in the orbital labels. And then in an octahedral complex, we'd have 6 ligand group orbitals, so sigma orbitals, something that has symmetry that would be pointed at the appropriate for sigma bonding to the metal d orbitals. Each of those ligands will have a pair of electrons. Okay, so this is the start of our diagram. Now we can determine the degree to which the ligands are stabilized by the interaction with the metal and the which d orbitals and the degree to which those d orbitals are destabilized in the sigma bonding interaction using this table. So the table gives you the positions of the ligands for octahedral ligand positions 1 through 6. So the diagram shows the positions around the metal, and then over here we see those ligands 1 through 6 on the left side of this table. We also have the ligand positions for any particular shape. For instance, linear has ligands at positions 1 and 6, trigonal at positions 2, 11, and 12, T-shaped at positions 1, 3, and 5, and we'll be able to use these positions for these particular shapes, and then this side of the table to determine the amount of overlap with the d orbitals at those particular positions. So this is how this works. For octahedral, we have positions 1 through 6, and just considering the dz squared orbital first. Okay, so the dz squared has strong overlap with the ligands in positions 1 and 6, and a little bit weaker overlap with ligands in positions 2 through 5. And that's indicated in the column under the dz squared orbital. 1, 1/4, 1/4, 1/4, 1/4, and then again 1. These are in units of E sigma, indicating the energy or the amount of overlap for a sigma interaction of the dz squared orbital with any particular ligand position. So obviously the ligand position 1 has a greater degree of overlap with the dz squared than ligand position 2. And we saw this type of effect when we looked at crystal field theory also. Okay, so ligand position 1 contributes 1 E sigma. Ligand positions 2 through 5, 1/4 E sub sigma, and then ligand position 6, another 1. So adding those up, we get a total of 3 E sigma as the amount that the dz squared will be raised in energy, and that's how we calculate that. So we'll draw in another dz squared raised in energy by 3 E sigma and above its original position before the interaction with the ligands. The dx squared minus y squared, we can also calculate its interaction with the ligand orbitals. Its degree of overlap is indicated in the column under the x squared minus y squared. And at ligand position 1, there's apparently 0 overlap, and so that contributes 0. The same for ligand position 6. But ligand positions 2 through 5 contribute 3/4 each in units of E sigma. And so adding those together gives you 3 E sigma, and so the dx squared minus y squared is raised by the same amount, 3 E sub sigma. So that is the degree of interaction of the ligand sigma orbitals with the dxz squared and dx squared minus y squared orbitals. And we show those raised in energy above their original positions. Now, the xy, xz, and yz have 0 overlap with ligands in these particular positions, and the positions for an octahedral structure. And so those are unmoved, and so we just move those orbitals over in our diagram at the same energy as their original positions here. Now, to calculate the degree of stabilization of the ligand orbitals, here we go across the table. So for instance, at ligand position 1, that ligand orbital will be stabilized by the dz squared by 1 unit, and by the other orbitals not at all, okay, 0. So 0 overlap of that particular position with those other orbitals. Okay, so the ligand orbital 1 is stabilized by 1 unit. At ligand position 2, that orbital is stabilized by its interaction with the dz squared and the dx squared minus y squared by 1/4 and 3/4. And so that's also 1 unit. And then ligand positions 3, 4, and 5 are stabilized by a similar amount, totaling 1. And then finally, ligand position 6 is stabilized by its interaction with the dz squared orbital. So all of those orbitals are lowered in energy by 1 unit. So I show those lowered just slightly. We'll draw dotted lines indicate the interaction of the orbitals, and there we go. And so this is your energy diagram for an octahedral complex based on the angular overlap model. So let's do a quick example using this particular diagram to calculate the ligand field stabilization energy for an octahedral D3 complex. To do this, we're going to show our ligand pairs of electrons stabilized each by 1 E sigma. So each ligand electron is stabilized. So 6 orbitals with 2 electrons each each stabilized by 1 unit, is a total of 12. E sigma is a total, the net energy benefit. We'll put a negative in front of that to indicate they are lowered in energy by that amount. If we have a D3 complex, those 3 electrons are going to be in the lower energy d orbitals, which were unmoved in the based on the angular overlap model, and therefore they're not going to contribute. And so our total ligand field stabilization energy is going to be minus 12 E sigma. Let's suppose we wanted to do a similar calculation for an octahedral high-spin D6 complex. In this case, we have 6 electrons distributed throughout the 5 d orbitals. We're assuming it's a weak field and therefore high spin, so the electrons fill in all the orbitals and only pair up in the bottom orbitals when needed. So now our contribution to the ligand field stabilization energy is again going to be from our ligand electrons, 6 times 6 orbitals, 2 electrons each, 1 unit stabilization, minus 12. And then the metal electrons, there's 2 that are raised by unit of 3 E sigma, and I see I've made an error here. And so that is a total of 6. That will be positive since they're raised in energy. And so the total ligand field stabilization energy is now minus 6 in units of E sigma for the angular overlap model. Okay, let's assume that we have pi interactions. And I'm going to stretch this diagram out because it'll be easier to show the pi interactions and show the change in the diagram. So this is the same diagram we were just looking at. I've just stretched out a bit, elongated it, so it'll be easier to see how the orbital energies change with the pi interactions. There's a separate table in your book, similar but separate table for the pi interactions. And for this first example, we're going to assume that all 6 ligands can participate as pi acceptors. So for instance, complex with 6 cyanide ligands, each cyanide can participate as a pi acceptor. In other words, in back bonding of electron density from the metal to the pi star orbitals of the cyanides. Remember, each cyanide has 2 pi star orbitals, which are empty, no electrons. Those orbitals with 6 ligands would combine to make 6 group orbitals, pi star orbitals. Those orbitals interact with the metal. We'll show a little diagram here to indicate the type of interaction that can occur. Here we have the metal. I've shown the x and y coordinate, so this is a dxy orbital in the metal with overlap to a pi star orbital of the cyanide ligand. And then of course the metal can dump electron density into the pi star orbitals from the metal d orbital. And this is called back bonding. Back bonding of d electron density to the ligand. We're going to use the table in the similar fashion that we did with the sigma interactions. And in fact, in creating these diagrams, I always start with the sigma interactions alone and then modify the diagram to take into account the pi interactions. So we're going in the exact order that I would have anyway, starting with sigma and then going on to pi interactions. If all 6 ligands can participate as pi acceptors, those pi interactions are going to have less overlap than the sigma interactions, and so they're given a different unit, E sub pi, and this is going to be smaller than the sigma interaction to take into account the smaller overlap of those orbitals. The dz squared has 0 pi interaction with ligands in positions 1 through 6 in our octahedral complex. So these 6 cyanides arranged in an octahedral fashion occupy positions 1 through 6, same positions we just worked on with our sigma interactions. But now in the pi interaction, the dz squared has 0 overlap with these types of pi star orbitals. And so this dz squared will be unaffected. And that holds true for the dx squared minus y squared. 0 overlap with the pi star orbitals of ligands in positions 1 through 6. However, the xy has strong overlap, pi overlap with ligands in positions 2, 3, 4, and 5. And those contribute 1 unit each for that overlap of E pi. So in a pi acceptor interaction, pi acceptor of the ligand from the metal, the d orbitals are lowered in energy, and so our dxy will be lowered in energy by 4 E pi. And then our dxz and dyz are also lowered in energy due to, for the dxz, interaction at ligand positions 1 and 2 and 4 and 6, and for the dyz at positions 1, 3, 5, and 6, each getting 1 unit for the degree of overlap at those positions. That totals also 4 E pi, and so those will also be lowered by the same amount as the dxy. And there you go. And so now we've completed our diagram showing the lowering of the d orbitals due to this pi backbonding interaction. I've shown in here the ligand pi star orbitals being raised in energy. Of course, those have no electrons in them, so they don't contribute to the overall calculation of the energy of the complex. And of course, this raises the ligand field splitting energy for a complex due to this pi interaction that we've added in. Now keep in mind, if you do a diagram, if you create a diagram in which you have pi donors, for instance a chloride or a bromide or iodide ligands, which can contribute pi as a pi donor ligand, in that case your d orbitals will be raised in energy. So whichever d orbitals you find have overlap with the ligands and the positions based on whatever particular geometry you happen to be studying, those ligands, those d orbitals will be raised up in energy by the unit of E pi, determined by the positions on the table. Okay, so for this complex, now our ligand field splitting energy is equivalent to 3 E sigma plus the additional lowering of these d orbitals by 4 E pi.